Hello, class. Welcome back to lecture 5. Today we're talking about compound inequalities. But first, I got to remind you what inequalities are in math. So they involve these symbols. So recall these symbols. There's this guy, the same one with the lines underneath. So what are these for? So they just say that one thing is bigger than the other, or one thing is less than the other, but you can also be less than or equal to or greater than equal to. So it's best just to see examples to remind you how these things work. For example, 4 is bigger than 2, so I can write this. And so what this is saying is greater than. This means greater than. And if I do something like this, -2 is less than 10, I could write this. So this means less than. So basically the guy that it's pointing to is the smaller one, no matter what. So you could think about the first thing as 2 as being smaller than 4. In this one, you could think of -2 as being smaller than 10. Whichever one the arrow is pointing to is the smaller one. And then you can also use the other symbols. So you could say something like this: 5 is greater than or equal to 5. And that makes sense to write because 5 does equal 5. So now what this symbol means is greater than or equal to instead of strictly greater than. So this makes sense to write, but if you write 5 is greater than 5, that does not make sense. It's not okay because 5 is not bigger than 5. 5 is 5. Okay, so we would never write anything like that. And then the last symbol that we have is you could use less than or equal to. So you could say 3 is less than or equal to 15. And that is fine as well. Less than or equal to. That's how you would say the symbol in the sentence. 3 is less than or equal to 15. So you could write that. You could write 3 is less than or equal to 3 is okay to write because of the or equal to part, but you would never write 3 is less than 3 because it's not. 3 is 3. Okay, so that's just reminding you how these symbols work. But now what we want to do is we want to bring the variable x into the game here. So what we want to solve inequalities. Instead of before, you might learn how to solve equations for values of a variable. That's the idea. So previously, you might solve something like 2x plus 10 equals 4 using algebra. You might solve something like this, and so what you're doing is you're finding the one value of x that works, that solves the equation. That's what you're really doing. And so you do some algebra rules to do it. So like you might subtract the 10 over and then divide by the 2. So then you say that x equals -3 is the only value of x that solves this equation, meaning if I put it back in, I will get 4 equals 4. But now, all we're going to do is replace the equal sign, the symbol equals, with one of the other ones. One of the 4 that I just reminded you about. And then we want to still solve for values of x. But what we'll see is instead of just saying x equals one thing, we're going to get a whole bunch of values that work for x. And so this is called solving inequalities. So first, what we're going to do is we're going to figure out how to interpret what you'll get at the end. So your result, when you solve an inequality, it'll end up with something like this. Something like, instead of saying x equals -3, you'll end up with something like x is bigger than or equal to -3, some number. But what does this mean is what we want to interpret. Because up here, what it means that -3 is the only number that will make the equation work. Any other number you put for x, it won't work. So this is really saying that any number bigger than -3 or equal to -3 will solve whatever equation, whatever inequality this came from. So this is really saying much more than just one number. This is saying all numbers bigger than or equal to -3, instead of just a single number is a whole bunch of numbers. And what we do is, if we want to list a bunch of numbers, we don't just write them out. Instead, we use some clever notation to list out all these numbers. So there's two ways to do it. So interval notation is the first way. So what we do is we say, okay, what's the biggest or smallest number we are allowing? And so if we want all the numbers that are bigger than or equal to -3, that means the smallest number we're allowing is -3. So interval notation says, okay, if I want to say all the numbers more than -3, what I'm going to do is I'm going to start with -3. So I'm going to start there, and then a comma, and then I'm going to go until I want to stop. So I want all the numbers bigger than or equal to -3. Well, to include all the numbers, what I do is I write the symbol infinity. So that means I'm starting at -3 and I'm including all the numbers bigger than it. And what we do is we write it in a little parentheses. And then on the -3, because we are including -3 in the count, what we do is, instead of writing parentheses, we write a square bracket. Okay, because of the equal sign. If there wasn't an equal sign, then it'll be a parentheses, which is what we'll see next. Okay, so just keep that in mind. It's easier to get once you do a bunch of examples and compare. So we'll get there. Okay, so then interval notation is one way to describe all the numbers bigger than or equal to -3. But you can also do it graphically on a number line. So the way you do it is you just say, okay, -3, that's where I'm going to start. And I'm going to put a bubble there. And because I want all the numbers bigger than it, that means to the right. So then I shade the right side. And then maybe I draw a little arrow to indicate it keeps going. Okay, so we'll see lots of examples to get used to this. And if it wasn't for this equal sign, then this would not be bubbled in. So we'll see an example of that right now. Actually, let me do the other direction first. So up next, we got, if I say something like x is less than or equal to -2, well, that means all the numbers to the left, less than whatever you're talking about, -2, or equal to -2. And so now the biggest I want is -2. And then I want to go to the left forever. So I'm going to put the infinity on this side of the -2 because I'm going less than it. But because we're going towards the negative direction, we call it negative infinity. And again, parentheses around the infinity or the negative infinity, and a square bracket around the -2 because of this equal thing. And then, so that's the interval notation. And then graphically, same as last time, except now, where I bubble -2 again, but I shade to the left to indicate that I want all the numbers to the left of -2. Okay, so now for comparison, what happens if it's not an equal to? So we're going to change this guy to not having an equal to, and then it becomes a little bit different, very similar. So if I do x is bigger than 1, this means all numbers above, aka greater than 1, but now I don't include 1. So 1 is just like the barrier, but I don't actually include the barrier this time in the count. So what I'm doing now is I'm thinking of 1 as my smallest number. So I want to start at 1 because I want all the numbers above 1. And then I'm going to go to the right forever because I want to include all the numbers above it. And so that's going to be the same as the first example, but on the left, I'm going to use a parentheses instead of a bracket. And this means that we're not including 1. If it was a bracket, then you would be including 1, and that would be for when it's a greater than or equal to. So this is the interval notation when you don't want to include the boundary. And then graphically, what we do differently is we don't bubble in 1. We leave it as an open bubble, an open circle. And then we still shade to the right because we're looking for all the numbers above 1. So with that in mind, you might be able to guess what this means. It means all numbers less than 10, not including 10. So you can think about it as less than or below 10, not including 10. So in the interval notation, the biggest number we're looking for is 10. So that's that on the right side, and we go to the left forever because we want all the smaller numbers than it. And that negative infinity gets a parentheses symbol. And now on the right, instead of a bracket, it's a parentheses. And that's because we are not including 10. And then you might be able to guess that graphically, the way we draw it is same as before. We put 10 wherever you feel like, and we don't fill in the bubble, and then we shade the left side because we're going forever to the left. Okay, so those are the 4 types of interval notations that we're going to need really for now. And so now we're ready to solve some inequalities. So let's do it. Next, solve inequalities. And so we're just going to jump right into it. Solve 2x plus 3 is greater than 7. 7 is a bit annoying because it looks a bit like a greater than, but that's a 7. Maybe I'll do that. So again, when I write something like this, what I'm really saying when I say the word solve is I'm saying like, say all the x values making this true or work correctly. And that's what algebra does for us. So the way we solve it is we sort of pretend it's an equal sign and we just do our usual things. So we just want to get x alone. So what I can do is I can subtract 3 to both sides. So I get 2x is greater than 4. And then I can divide by 2 on both sides. And so this answers my question. So what are all the x values that make this inequality work? Well, the answer is any x value bigger than 2. And then we write those numbers in interval notation. So any x value greater than 2 solves the inequality. But we get tired of writing that sentence every time. So what we do is we use interval notation to say that all at once. That's the point of interval notation. So we just say the lowest number is 2, and any number bigger than that, so I can go all the way towards infinity, works just fine. So that's the start of it. And then I put parentheses around the infinity because I can never actually include infinity. So I would never use a square bracket there because it's not actually a number. And on the left side, I got to decide based on this symbol, do I include 2 or not? I don't, because it's not a greater than or equal to, it's just greater than. So it's just a parentheses. 2 is not included. And then graphically, I can also say the same numbers by what I did before. So here's 2. I don't bubble it in, and I just shade to the right. So all I'm doing is saying all the numbers bigger than 2 in 3 different ways. This is the first way. That's just saying it. This is the second way in interval notation, and then this is the graphical way. That's what we are expected to do. Okay, so it does get a little bit tricky in one situation. So once again, I'm saying solve, but I mean so much more. It means find all the x values that make this thing true. And the way to do it is use algebra. So what we're going to do is get x alone. So I can subtract this 4 over to start. And then I can divide by this -3, but something interesting happens. When you divide or multiply by a negative, the inequality switches direction. Very important thing to do. So this becomes x less than or equal to. So we switch this direction and then proceed, and we're good after that. And now we write our answer in interval notation. So this is saying that the biggest number I want is -1/3, and I want to include it because of the equals, and then I want to go to the left towards -infinity forever. So that's why it's that. Okay, so again, this means include -1/3, and it's because of this equal sign here, this less than or equal to. And then graphically, do that too. So I'm starting at -1/3 and I'm including it because of the equal sign, the less than or equal to, and then I'm shading to the left. So it's always good to just think about what's really going on. So this is saying like only numbers to the left of -1/3 will make this inequality work. So if I plug in 10, for example, let's just see what happens. It should not work. What does that mean? It should not work. Well, you should get something that doesn't make sense. That's what it means to not work. 4 minus 30 is greater than or equal to 5. So -26 is greater than 5. Is that true? No. There's no way a negative number is bigger than a positive number. So that's what I mean by when I say works. So numbers to the left of -1/3 will make something pop out that makes sense. Numbers to the right of -1/3 will make something like this happen where it doesn't make sense. Okay, so we're solving for the ones that make sense when we do this. And then we're writing them in interval notation or graphically. Okay, so then lastly, we sort of up the complicatedness of it by solving the title of this lecture. Next, we solve compound inequalities, which is only slightly harder than what we've been doing, but it is harder. And what this means is we solve more than one at the same time. And they are attached by, this is going to sound weird at first until we see some examples, by the words or or the word and. So it's best just to see an example, not to worry about that too much until I do an example. These have specific math definitions. So we're just going to jump right into an example instead of worrying too much. So what I mean is we're going to solve something like this. So it'll be written like this: 5 minus 3x less than or equal to -1, or 8 plus 2x is less than or equal to 5, something like this. But the word or here has a very specific math definition that's hidden, different than English. It's more precise. What this really means is, and it's like hidden, it means that solve for x values that solve either equation, either inequality. That's what the word or really means in math here. So what I'm looking for is I'm looking for x values that solve either inequality. So all I'm going to do is solve both of them as my first step. Okay, so solve them both. Then say the x values that work for either one. Meaning it doesn't have to work for both, it just has to work for one or the other. Okay, so I'm just going to solve them both side by side. They're not affecting each other at all. So on this guy, I'm just going to subtract 5 on both sides. And then I'm going to divide by -3. And remember, dividing by this negative makes it flip to the right. And so I get this. -6 over -3 is 2. Okay, and then over here, I'm solving 8 plus 2x is less than or equal to 5. So I'm going to subtract the 8s on both sides. And now I have 2x is less than or equal to -3. And I'm dividing by 2, which is not a negative number, so I don't have to worry about flipping anything over. So then the point is that my answer to this question of which x values solve either one equation or the other is really this. Either x can be greater than or equal to 2, that's fine, or x's that are less than or equal to -3/2 are also fine. So to finish it off, what we do is first, we'll think about it graphically instead of as intervals. So graphically, this is saying that as long as the number is bigger than 2, that's okay. But it's also okay if a number is to the left of -3/2. And if I want to see all the numbers that are okay, all I have to do is put them on the same line. But I got to make sure they're in the right order. So -3/2 should be to the left of 2 because it's negative. So I'm going to put -3/2 over there, 2 over there, and then I'm going to do my shading again. So being to the left of -3/2 is good. So I'm going to shade that side. And being to the right of 2 is good. So I'm going to shade that side. And now I can write it as an interval I have to use some fancy math language though. As an interval, what I'm saying is I can go up to -3/2 and I can include it. So I do a square bracket and then I can go forever to the left. So that's what that means. Or I can start at 2 and go all the way to the right forever like that. But instead of writing the word or, we write this symbol called a union, and it just stands for or, really. So this is how you do an interval if you want to combine 2 together, which is what's really going on here. We're taking our 2 intervals and we want to write them as some sort of combination. We put this U symbol to mean or. So the x values to the left of -3/2 are fine. So are the ones to the right of 2. Either or is fine. So we write it like this. Okay, so then this last example is sort of the opposite of this example. So I said you could use the word or, but I also said you could use the word and they have very specific math definitions. So the other type of thing you'll get is something like this. Solve 6x minus 3 is less than 9. And instead of or, 2x plus 9 is greater than or equal to 3. So this word and means something different than the word or. Now what this is secretly saying is that we want x values that work for both at the same time. So solving one is not good enough. That's what or is for. Or says you could solve either one and that's cool. That counts as good. But for and, we only want the x values that solve both at the same time. If you solve one but not the other, that's not good enough. So what we're gonna do is we're gonna solve both and then put them together. Okay, so it still starts the same way as last time, meaning we just solve both to start. But what we do after that is a bit different. Okay, so on this left one, I'm gonna add this 3 over. So that gets me 6x is less than 12, divide by 6, x is less than 2. And then on the right, I solve that one separately. So I subtract the 9 over, 2x is greater than or equal to negative 6. And then divide by 2, x is greater than or equal to negative 3. So what this is saying is the x values, which are both less than 2 and bigger than or equal to negative 3, are the ones we want. Those are the ones that work. And how can I visualize that? Well, what I can do is I can, once again, draw them together. So first of all, I'm going to put them in the right order. So negative 3 is to the left of 2. And then I'm going to look at each one. So this is saying I only want the x values that are bigger than or equal to negative 3. So I can include negative 3, and then I can shade forever to the right. But unfortunately, this one has a disagreement. This one is saying, well, actually, I only want numbers that start at 2, not including 2, and then go to the left forever. So which x values work for both are just the overlap, which is what's in here. So when you see the word and, what you're looking for is the overlap, really, when you draw the picture. So the actual graphical answer would be this. So negative 3 is okay. And then I'm allowed to go as far to the right as I want, except I cannot actually be negative 2. So I got to stop there. So it looks something like that. So I'm just shading in between negative 3, sorry, a positive 2. I accidentally changed it. And then I'm not filling in 2, and that's really because of this not having an equals. And I am filling in the negative 3 because that one does have an equals. So that's how and problems will always work. And then once you have that, then it's a little bit easier to write it as an interval, but it's a bit different than what we have been doing. So as an interval, this is saying I can go to negative 3 in the left direction, and in the right direction, I can only go up to 2, but I don't include 2. So there's no infinity stuff here because we're just going between two numbers instead of going all the way to one side or all the way to the other side. Okay, so that's it for this lecture. I will see you next time.